Yeah. Hi everyone, welcome to today's class. Hi everyone. So we're starting and welcome to today's class. You already know that Dr. Aziz is on travel, so he's actually in Europe. So that's why I'm here. I'll be taking today's class. So my name is Shamil Alam, and I am one of Dr. Aziz's PhD students. So in today's class, we'll learn about these cryogenic memory technologies. So I think you have already learned about different memory technologies like SRAM, DRAM, and flash, right? And in next classes, you will also learn about different emerging memory technologies as well. But unlike those technologies, cryogenic memory is not a specific technology, like SRAM is one technology, right? So cryogenic memory is not one technology, but you can consider it as an umbrella of different technologies that can operate at a specific environment, right? That environment is that cryogenic, which is extremely low temperature. So let's first discuss what is cryogenic. So before today's class, maybe you have taken lots of electronics courses, right? Even in this course, you have learned about different technologies. But if you remember, all of those were for room temperature only. You by default assume that the temperature is 300 Kelvin, right? But in addition to that, there are two other extreme conditions. One is if you start going to lower temperature, like this, if you go to lower temperature, that's the cryogenic environment. And there is another extreme, which is if you start increasing the temperature, there is that high temperature electronics field. But in today's class, we'll only talk about the cryogenic environment. And maybe in one of your future courses, you'll also learn that high temperature electronics field, hopefully. So now the question is how low temperature is considered as cryogenic, okay? So theoretically, any temperature below 100 Kelvin is considered as cryogenic environment. And then how do we achieve this low temperature, okay? So we actually use cooling refrigerator, like a literal refrigerator we use to achieve this low temperature. And you see there are different temperature ranges that you can achieve in that cooling refrigerator. And to achieve that, you will have to supply different elements. Like one of them is liquid nitrogen, liquid helium. There are other elements like that you need to supply. And those are referred to as the coolant. And you'll have to keep supplying them to maintain that low temperature in that refrigerator. So among these different temperature ranges, two actually are the most famous. One is 77 Kelvin, which is liquid nitrogen. You can use directly liquid nitrogen. You can keep supplying that. That will be your 77 Kelvin. And another one is 4.2 Kelvin, which is the liquid helium temperature. Again, similar approach. You'll have to just keep supplying liquid helium to the refrigerator. That will be your 4.2 Kelvin. And you can see that you can use direct liquid nitrogen and liquid helium. So it's easier to achieve. That's why these two temperature ranges are mostly used. If you look at any literature on cryogenic environment, you see mostly these two temperatures. And recently, another temperature range is most famous. You can say that's like in the millikelvin range, which is in here 20 or 30 millikelvin temperature, because there actually qubits are placed like quantum computer. You might have heard about that term, right? The qubits are placed at that extremely low temperature, millikelvin temperature. So these are the most famous temperature ranges you can consider. And when you read, like go to these temperatures, you can also achieve that intermediate temperatures and you can do your measurement there as well. But 77 Kelvin, 4 Kelvin, and the millikelvin, like 20 millikelvin, are the most famous cryogenic temperature ranges. Now, the question is why we need cryogenic electronics, why you need to spend a huge amount of cooling cost to achieve this extreme temperature, okay? So there are two major motivations. The first one is that we actually see improvement in different performance metrics, like we care about speed, energy efficiency, right? So when you go to this low temperature or cryogenic environment, we see improvement in this performance metrics. That's one motivation. And another motivation is that there are specific fields where you need these cryogenic circuits and systems. You cannot use room temperature circuit systems there. So these are the two motivations. And in this slide, you can see that, again, in the scale, you can see that the more you go to this cryogenic environment, like lower temperature, you see we are achieving higher and higher speed. And also the energy requirement is decreasing, right? So if we compare with the room temperature here, for example, if we go to this liquid helium or 4.2 Kelvin temperature, we are getting 1,000 times more computing speed. and also we are needing 100 times less energy. You see, this is a significant improvement, right, compared to the room temperature. And again, if you go to the 30 millikelvin temperature where you place the quantum computer like qubits, you see we get 1 billion times more processing speed. Also, we need like 1 million times less energy. You see, these are really significant improvement, although you need to spend a huge amount of like money to achieve this like cryogenic environment in the refrigerator, right? The cooling cost is there. But you see the improvement in speed and energy efficiency is really significant, and that's why people are exploring these fields, because we are also looking for alternative to our room temperature CMOS technology, right? Because we cannot do too much about their further improvement. We have almost reached the fundamental limits of scaling. So people are exploring this cryogenic environment as a viable alternative to that. Okay. And the second motivation, as I mentioned, there are specific fields that actually need cryogenic circuits and systems. These are the three major fields that can highly benefit from cryogenic electronics. I'll talk about this one by one. So let's start with the most exciting one, which is quantum computing. Okay. So you might have heard about quantum computer at some point, because this is now a very hot topic. And the major advantage of quantum computers is that they can solve the limitations of our classical computers that we use. Okay. So the primary problem with our classical computer is that you have very high computing speed, like computing capability, but it's still limited when you try to do some optimization problem, like large scale optimization problem. Also, if you want to simulate like large scale molecules for drug discovery or other applications, that their capability becomes limited, right? You need an unrealistic amount of time, like 100 years, to solve some of those problems with classical computers. But if you have a quantum computer, you'll be able to solve those problems within a day, maybe. Okay. So recently it has been shown that like quantum computer can achieve like 66 million times faster computing capability, you see. So this is the major advantage. And if we have a quantum computer like with reasonable number of qubits, that can revolutionize different important fields. And the major difference again between classical and quantum computer is that it's from very high level perspective. You know, in classical computers, we have bits to like represent the information, right? And we know we have only two possible conditions, 0 or 1. And we can be in either of these states. We cannot be at the two states, like both these states at the same time, right? We can either be at 0 or at 1. But in quantum computer, instead of bits, we have these quantum bits or qubits. Okay. And you see, we have this 0 and 1 like the classical computers, but we have like other combinations as well. So this is represented by this sphere actually. So if you are in the top pole or this bottom pole, that's like the classical computers. You are either at 0 or 1. But unlike the classical computer, you can also be inside, anywhere inside this sphere. That means you can be at the same time, you can be at the both of these states, and you will have a probability of being at 0 and of being at 1 at the same time. Okay. So if one of the probability becomes 0, that means you are like in the classical domain. But in most of the cases, you see that there will be probability for both 0 and 1. That's the quantum phenomena, and that phenomena is known as superposition. Okay. And you can see due to this superposition phenomena, you have actually unlimited like number of possibilities, right, for the qubit states. And that's the advantage. When you do any computing with these qubits, the qubit can actually consider unlimited amount of condition at the same time. And that makes them really superior for the optimization problems or all the other large scale problems. Okay. So that's the major advantage. But there are some challenges. I'll discuss about them. So currently the quantum computers that we have, there are three major components. One is the qubits. I have already explained that they are primarily responsible for any computing. So there you use the quantum phenomena like superposition, entanglement, and others. And with that, you still have some classical like components. Like to control these qubits and also to read out and store the qubit states, you still need some controller and a memory system. And these are classical. These are not quantum. Okay. So only the qubits are quantum, and you still need these classical components. And again, the existing quantum computers that we have, as I mentioned, the qubits are placed at really low temperature, which is in the millikelvin range, because they are extremely sensitive to external noise. So if you go to this lower temperature, thermal noise and other noise will also decrease, right? That's why to save them from these external noises, they are placed at extremely low temperature. But in the existing architectures, the other classical components, control processor and memory, they are placed at room temperature. So you can easily imagine now to connect these classical components with these qubits, you will need a huge amount of wires and interconnects, right? To make this connection between the room temperature components and the millikelvin qubits. So this is another one major challenge. Now, if you want to increase the number of qubits that you want to have, like to achieve more computing capability, you will have to increase this number of qubits. And for that, the number of wires and interconnects will exponentially increase, and that will limit the scalability of the whole quantum computing system. And also another challenge is there when you use these wires and interconnects, you see these wires have like a large temperature difference between the two ends. At one end, it has 300 Kelvin, and at the other end, it has millikelvin. So temperature difference is almost 300 Kelvin, right? So that will cause heat dissipation, right? From high temp, we know that heat always dissipates from high temperature to low temperature. So that thermal noise will actually dissipate to the qubits through these wires. Now, if we again increase the number of wires and interconnects to achieve more qubits, the resultant heat dissipation will be sufficient enough to destroy the qubit states. So there is no point of keeping the qubits at millikelvin temperature, because wires will actually take those heat thermal noise to the qubits, right? So these are the two major challenges why we cannot actually have like thousands or millions of qubits in the quantum computing system. And also another challenge is there, since we place the controller and memory at room temperature and qubits at millikelvin, we need to use one dedicated control line, as you can see in this figure. To control one qubit, we are using one dedicated control line, right? So, and that's again because of these long wires. If we combine all the control signals together, that might get destroyed through these wires and interconnects because of losses, right? And for that, we also need like more number of wires and interconnects, because we are using one control line for one qubit. And you can see that it's from one recent report. They, to control one quantum computer, a quantum computer with only 53 qubits, they needed 200 coaxial cables, 45 microwave circulators, and a rack full of electronic circuit. You see, now if you want to have thousands of qubits, you can easily imagine the overhead from the classical part, right? And that's solely because of using that room temperature component. And that's and also, as I mentioned, we actually need thousands of qubits in a quantum computer, because, for example, if you want to run Shor's algorithm for prime factorization on a 1000-bit number, you need more than 3000 ideal qubits. And we don't have that in any of the existing quantum computers. IBM has like around 400 qubits, okay? So, but we don't have thousands of like qubits. And also we need ideal qubits. The qubits that we have currently, those like suffer from lots of errors. So, and to do the error correction for one qubit, we need additional like 9-10 qubits more. You see, so to have 33,000 ideal qubits, we will need maybe like 30,000 like the existing qubits, and that's impossible with the existing architecture. That's why the goal is to take all these classical components to cryogenic temperature, which is more preferably the 4 Kelvin temperature, so that we can place them very close to the qubits. And in that way, we will be able to reduce the amount of wires and interconnects that we need to make the connection. And another advantage we will get here, so if we go to this 4 Kelvin temperature, there we can use superconductors. So how many of you are familiar with superconductors? Right? So so you are familiar with semiconductor. There you have two different resistance states, but superconductors has a state where you have zero resistance. That means you don't have any, like, like heat energy is always represented by I square R for any wire, right? So if you don't have any resistance, R equals 0, that means you don't have any heat dissipation there. So at 4 Kelvin, you have lots of superconducting materials, and you can use superconducting wires and interconnects to make this connection. And that will solve your heat dissipation issue as well. Okay, so you can take all these advantages if you have a suitable cryogenic control processor and a cryogenic memory system. I mean, combinedly the cryogenic electronics. Okay, So then you will be able to scale the quantum computers up to thousands and millions of qubits. And another possibility is there. People are also exploring that because the 4 Kelvin with liquid helium is really expensive. And another possibility is like 77 Kelvin or liquid nitrogen. And if you compare this, 4 Kelvin temperature is like more than 200 times more expensive than liquid nitrogen. Okay, that's why people are also exploring that to save some cost. Again, the challenge is there here. You cannot have superconducting interconnect at 77 Kelvin, so you will still have some heat dissipation, although that's lower than the room temperature condition. And also the amount of wires and interconnects you will be needing, that will also be like significant amount, because for like millikelvin and 77 Kelvin, there's also you also need that wires and interconnect. So with this 77 Kelvin option, you will get better scalability than room temperature, but that will not be the best case. So best case will be the 4 Kelvin or lower. Okay. So and for both these cases, like 4 Kelvin and 77 Kelvin, you cannot use room temperature circuits. You need the cryogenic electronics here. Another major requirement for quantum computing is again, this course is about memory. So we are now going into the more focus into the memory system. So the classical memory that we need for quantum computer, we need very high capacity memory, because to do any computation with the qubits, we need to run these quantum algorithms, which include large number of arbitrary rotations and also sending different shapes and different signals to these qubits. And we'll have to store all this information into the memory when we want to send them to the qubits, right? So for that, we will need a large program memory in the memory system. And similarly, as I mentioned, the qubits that we have, they suffer from lots of errors. That's why after doing every computation, we need to do this continuous error correction. And for that, we also need to store the information about the error type, the correction mechanisms for each of the error types in the memory, which needs large data memory. So combinedly, we will need a very high capacity memory for quantum computing applications. So these are the two major requirements. We need cryogenic circuits and also high capacity memory if we focus on the memory system. The second field we are going to talk about is high performance computing. And as you already know, I think Dr. Aziz has already talked about this because that's the main motivation of like learning about the memory system. We are now generating a huge amount of data, right? Every second. We are using ChatGPT and other AI tools. We are using social media through which we are generating a huge amount of data every second. And you can see that here, the amount of data is actually increasing exponentially every year, right? And also and that's why you can see that here it's been projected that the data center, the green region here, will actually experience the highest amount of increase in energy consumption in the next few years. So we need like better technologies than CMOS, or we need to we need to keep improving the CMOS technology. But again, as I mentioned, one of the major challenges for CMOS technology is that we are almost at the end of this fundamental limit of scaling. Like we cannot do too much about further improvement of their performance. That's why you can see that here it has been projected that none of the conventional or CMOS based supercomputers cannot achieve the DOE's exascale goal, which is the pink diamond here. So this goal is like to achieve this 10 to the power 18 flop per second performance with 10 to the power 7, like 10 megawatt of power. And you can see that none of the conventional supercomputers, which are the red circles and red squares, they cannot achieve both at the same time. Some of them can achieve the performance, but they need much higher power than the budget. But the scenario is different for superconducting technology, which are shown by blue circles here. You can see that they can achieve the performance even with much lower power requirement than the budget. And the reason behind that is the extreme energy efficiency of superconducting electronics because of that zero resistance behavior, right? So they are extremely energy efficient. And in this figure, you can see that the superconducting electronics is outperforming by CMOS technology by significant margin in terms of both switching power and switching delay. And to mention the number, superconducting devices and circuits operate hundreds of gigahertz frequency, and they need like attojoule of power for switching. You see, like there are significant like 5-6 orders of magnitude difference if you compare them with the CMOS technology. So that's the major advantage of superconducting technologies. And like with the emergence of AI and other data intensive applications, these superconducting technologies can be an option, but you'll have to keep in mind that there will again be cooling cost to achieve that 4 Kelvin temperature. And finally, cryogenic electronics can also be a natural fit for space electronics. You see the deep space here. There you have the cryogenic environment for free, right? You don't need to, again, here, you don't need to use any cooling cost. So if you have a suitable cryogenic electronic system, you can use that to explore this deep space. And again, currently people use the same room temperature circuits and they send them to this deep space. And in some cases, it's observed that many of the circuits actually don't work because they're built to work at 300 Kelvin, not this like 2 Kelvin, 3 Kelvin temperature. But if we have like cryogenic electronics or other superconducting electronics, you can, they are made for this temperature, right? So you will have like different advantages. And again, like you can take the advantage of this cryogenic environment for free here. So that's why people are exploring lots of things at cryogenic environment. Memory, people are trying to design cryogenic memory because you need that for quantum computing or other applications. People are also doing cryogenic logic circuits for developing better processing unit. There are works on cryogenic oscillator and other analog circuitry. People are also doing neuromorphic system, cryogenic neuromorphic computing. So neuromorphic, again, I think all of these are familiar, but neuromorphic might be new term for some students. So neuromorphic is like to mimic the behavior of human brain, like how we compute in our brain, how we learn things. And we want to mimic that in circuits and in our electronics, in hardware. That's the neuromorphic computing. And people are also exploring that for cryogenic neuromorphic computing, because one of the major motivation for neuromorphic computing is to achieve the energy efficiency of human brain. Okay, and the superconducting electronics, you cannot beat them in terms of energy efficiency. There are no better technology that can give you better energy efficiency than superconducting electronics. So it's an obvious choice to use superconducting devices or technologies to design neuromorphic circuits for this cryogenic environment. So again, in today's class, we will mostly focus on this memory paradigm, again, targeting the cryogenic environment. So again, people have explored all the possible technologies you can imagine for cryogenic environment. That includes the non-superconducting memories that you are going to learn in this course, right? Like the charge-based SRAM, DRAM, flash. Then there are resistance-based memories like memory stick, spintonic, ferroelectric, all those. So what in terms of non-superconducting memories, these are actually again built for room temperature applications. But what people have done is they have taken the same circuit, they have not modified the circuit. They have taken the same circuit and they have placed them in the refrigerator in that like 77 Kelvin, 4 Kelvin at different temperatures, and try to verify if they work properly or not and how their performance changes. So that's the primary goal for this non-superconducting part. And again, superconducting is the new field where they have tried to design the memory from scratch using this superconducting device. And there is another approach, which is hybrid approach, because as I will explain, both non-superconducting and superconducting has different challenges for cryogenic applications. So people have tried to combine their advantages in this hybrid approach, where they have used both superconducting and non-superconducting technologies together. So we'll start our discussion with non-superconducting memories, and we'll start with the charge-based memories like SRAM, DRAM, and flash. So if you remember, I think you have already learned about DRAM and flash in this course, right? So if you remember in DRAM, the most simplest one is 1T, one capacitor, where you have one transistor, one capacitor connected in series. And in the flash memory, you have only one transistor, right? So if you think about these two technology, and also SRAM, right? There you have 6 transistor. So the performance of all these memory systems actually depend on the transistor, right? So transistor is the main like driving factor here. And that's why you see this is a nice illustration, and it's taken from one of the paper from IBM. IBM actually first characterized the DRAM at cryogenic environment in 1980s. So in that paper, they mentioned all this improvement in performance. So when we take the transistor, like same CMOS transistor at too lower temperature, again, this is not for 4 Kelvin, this is only for 77 Kelvin. Okay, so they went to 77 Kelvin and measured all those characteristics. The first thing is like, you remember the carrier mobility, right? For any semiconductor or semiconductor devices, and that actually determines the speed, like the switching speed of any semiconductor device. And you might also learn that in like solid state physics courses that the mobility is actually depends on temperature, right? If you reduce the temperature, the mobility will increase. And that's what you can see here. At lower temperature, you have higher mobility. That means you will have higher speed. Okay. And the next thing is you also know that resistance is also dependent on temperature, right? If you go to lower temperature, resistance also decreases, right? There is a like direct relationship between resistance and temperature. So if you consider the wires and interconnects that you need to make connections, there you have the resistance, right? In the metallic wires, you have resistance there, interconnect resistance. So that will also be lower at cryogenic temperature. That means again, higher speed, right? Because if in the wire you have this RC delay, right? That comes from the wire resistance and the wire capacitance. So at cryogenic temperature, this wire resistance decreases. That means the RC delay will also decrease. So you'll have higher speed there. And finally, you also, I think, remember the IDVGS curve of a transistor. You have something like this rough drawing. So you have this threshold voltage, right? After threshold voltage, the transistor turns on, and before that, the transistor remains off. So you have this threshold voltage, and the VDD that you use for like different circuits, you'll have to use the VDD larger than the threshold voltage, right? You want to have both, like off condition and on condition. So this VDD threshold voltage actually dictates the choice of VDD in your circuit. Now, when people take these transistors at cryogenic environment, they see that this threshold voltage actually decreases. So you have IDVGS curve like this. So VD becomes lower. Okay. And another advantage is there, like the threshold swing, sub-threshold swing that you have, sub-threshold slope, that also becomes sharper. So you reach the on current faster than compared to the room temperature, right? So if you have sharper turn on, that means you will have higher switching speed. So you'll have reached the on state faster. So your speed will be higher. That's one advantage. And again, if the threshold voltage becomes lower, then you can use lower VDD, right? Compared to room temperature, you can now use lower VDD. So if you have lower VDD, that will help you to get lower power consumption, and that will also help you to improve the reliability. Because if you remember in flash, when you apply very high voltage, that actually causes some failure. If you apply that voltage again and again, that causes breakdown in the floating gate, right? And that causes some failure. Now, if you can reduce that voltage or that VDD, that will help you to improve the reliability, right? So these are the advantages here. And another advantage is like if you plot the same curve in the log scale, you see there is some off current, right? Ideally, there should not be any current when the gate voltage is 0, but there are some current, right? We call them off current or leakage. And when we take the transistor to cryogenic environment, that leakage also decreases, the off current decreases. Right now, if you have less leakage, again, we will have lower power consumption because less leakage again. And another advantage is that if you remember again DRAM, so when you store some data into the capacitor through some charge, and if you turn the transistor off, right? So the capacitor cannot like store the charge for a long time because of that leakage, right? The capacitor starts discharging through that off current or the off state or through the leakage of the transistor, right? So that's why you need to refresh the capacitor after a few milliseconds, right? That's one of the major challenges. You cannot use DRAM to store the data for a long time because the capacitor will discharge through the leakage, and it will it will forget the data that you stored there, right? That's your retention. You remember, I think these terms, right? Endurance and retention. So retention is related to that long-term storage time. So now if you can reduce this leakage, the capacitor will be able to store the same charge for a longer amount of time, right? Because the leakage or the discharging will be now slower. So you'll have longer retention time. Okay. And finally, if you go to lower temperature, as I mentioned, the thermal noise will be lower, and similarly thermal wear out and thermal electromigration will also be lower, right? These things will be lower with the lower temperature. So it will also help you to improve the reliability of the whole circuits and system. So as you can see that, like if we go to cryogenic environment, we only get like good news, right? So everything improves, and that's the case for CMOS actually, right? And that's for 77 Kelvin, not for 4 Kelvin. So 77 Kelvin, people in some cases you see that like people actually claim that 77 Kelvin is the most ideal operating condition for semiconductors and CMOS circuits and devices. Okay, that's why we get all this improvement. And that's why actually you see when we take this DRAM, like flash, all those memory systems, like room temperature memory systems to cryogenic environment, we get improvement in performance. So as I mentioned, IBM first characterized their DRAM chips at cryogenic environment in 1980s. So they did again at 77 Kelvin range. So they more specifically, they went to 80 and 80 Kelvin and 85 Kelvin with their DRAM chips, and they observed that their speed actually improves compared to the room temperature. And then in 2005, another research group, they actually characterized the 3 transistor DRAM. I think you also know that another variant of DRAM, right? 3 transistor, where you have these 2 additional transistor to achieve separate read-write paths. So they took this 3 transistor DRAM circuit, and they reported that their speed actually improved by 40%, and they needed 30% lower power consumption, right? That actually, like, that actually proves all the theories that we have discussed so far, that at cryogenic environment, all the performance metrics should improve. And in the 2017, one group actually they didn't design any circuits. They actually bought 750 DRAM chips from 6 different major industries like Micron, AMD, Intel. They bought those chips, and they just took the same chips to different cryogenic temperature ranges. And they went down to 80 Kelvin here. And they mentioned that around 98% of all those 750 chips actually worked successfully. And they only cared about like proper operation, not any other performance metric. So they only reported that 98% of their chips worked properly at that low temperature. There is another work which again took the 1T1 capacitor DRAM, the simplest one, to 77 Kelvin. Again, they focused only on quantum computing applications, and they claim that the 77 Kelvin can be an option because this is much cheaper. And they showed that, like again, DRAM, for DRAM, the leakage, as I mentioned, the leakage becomes lower. So you have like longer retention, and you need like less amount of refresh. So you have all these advantages in terms of energy and power consumption as well. Then about flash memories, there is only one work so where they took the same room temperature flash memory, and they characterized it at 80 Kelvin again, because people mostly target 77 Kelvin. Like you might ask, why 80 Kelvin? Why not 77 Kelvin? So people mostly target the 77 Kelvin using liquid nitrogen, but in some cases they cannot go to the final temperature. Okay, that might be error from the instrument they use, also impurity in the liquid nitrogen, that there might be different reasons, but you end up somewhere near the 77 Kelvin. That's why you see 80 Kelvin, 83 Kelvin. That's the exact temperature. So they took their flash memories to 80 Kelvin, and in that way, they actually did the measurement at different temperature ranges. So if you remember, for flash memories, we mostly care about retention time, right? After we store the data, how long it can keep the data intact, right? That's why we use flash memories, even if we need that like tens of volts of voltages. So we have 2 types of retention time here: static retention time and dynamic retention time. So static is when you store something and you don't do anything. You just keep the flash memory as it is, and you measure, like you determine how long it can store the data. That's the static retention time. And dynamic retention time is you store the data, and then you just do read operation. You don't do any write operation. You read the data, and you determine how long it can store the data. So you can, that's why you can see that like static retention time is longer in every cases than the dynamic retention time, because when you do read, you actually affect the memory system. That's why retention time becomes smaller. And as you can see in the first figure here, in the middle figure, if when you go to this low temperature, both the static retention time and dynamic retention time actually improves, right? So that's again good news for flash memories. And another performance metric they considered is like sense margin. I think you know that when you have flash memories for 2 states, in one state you have electrons in the floating gate, and in another state you don't have electrons in the floating gate. So for these 2 states, you have 2 different channel current, right? So the difference between these 2 levels of channel current is known as the sense margin here. And as you can see here, if you go to lower temperature, that sense margin also improves. So you will have like more reliable and more robust read operation from this flash memory. So then we will move to the resistance-based memories here, and we will consider these four major technologies. I think, have you learned about the memory strip RAM yet? I think, okay. Then, so I will talk about memory strip RAM, ferroelectric RAM, spintronic RAM, and the final one is the topological memory. So the first three is actually again for room temperature. People have mostly designed them for room temperature, and you will see the same trend. So they will take the same circuit and they will measure them at cryogenic environment. And the fourth one, the topological memory, is actually actually needs cryogenic environment that cannot operate at room temperature or at higher temperature. Okay, so I'll talk, but the working principle of all these four memory technologies are similar. That's why they're in the same category here. So I'll quickly go over the memory strip memory. Okay, so we know that in memory strip memory we have these two resistance states, right? HRS and LRS, high resistance state and low resistance state. So for HRS we have lower amount of current, and for LRS we have this high amount of current. So these are the two states in memory strip memory. And initially the device remains in the high resistance state because there is no conducting path between the two electrodes because of that oxide material in between. Like we typically use hafnium oxide, but there are other oxide like tantalum oxide, titanium oxide you can use there. But because of that oxide material, which is insulator, you don't have conducting path between this electrode. That's why you have that high resistance state. But if we apply if we apply a high enough voltage and cross a certain threshold, you can actually create a conducting path like this. Then the device will switch to the low resistance state of the memory store. And then if you reduce the voltage and cross a negative threshold, you can again break this conducting path and the device will switch back to its initial high resistance state. And you can do this switching one after another in the repeated fashion. So that's actually your write operation. So if you apply a positive voltage greater than this threshold, the device will go to the LRS state, which is write 1. And if you apply a negative voltage less than -1, the device will always go back to the high resistance state, which is your write 0. So this is your write operation. And read operation is like if you apply a voltage in like less than the switching threshold, then based on the resistance state, you can get either get this lower current or this higher current. So two levels of current. Again, if you compare between these two levels of current, you can detect the memory state stored in the cell. So that's your write and read operation. And again, there are advantages. Major advantage is this memory strip memory is non-volatile. Okay, you can see even if you remove the voltage, it can remember the resistance state it was in. Oh, so that if you store the data and if you again remove the voltage, it will remember the data, unlike the SRAM and DRAM, right? So it's non-volatile, and it has all the other advantages like high endurance, high retention time. So unlike like in SRAM, DRAM, you have better endurance, but like very poor retention. In flash, you have very high retention but very poor endurance, right? You remember that. That's why they cannot be used for same applications. We use SRAM DRAM for cache and flash for long-term storage. But these resistance-based emerging memories like memory storage, spintronic, ferroelectric, all of those has like high endurance and high retention at the same time. So you can use them for all the applications that you have in a computing system. So what people did again, like they took the same room temperature memory store. They mostly took the hafnium oxide based memory store and they measured at different cryogenic temperature. And again, from the memory perspective, for a memory store, we care about these two resistance states, LRS and HRS, because they actually determine the level of read currents that you will get during the read operation. So that will determine the read performance. And we also care about the switching thresholds that you have, set and reset voltage, because that will determine your write voltage and eventually the write power consumption. So these are the four major characteristics we care about from memory store, and there are like endurance and retention as well that we care about. So people actually measured all those things, and you see in the first case, actually the on-off ratio becomes lower than room temperature. That means it's like it becomes worse compared to room temperature at this 40 Kelvin temperature. And in the next one, where they use different electrodes, but the same hafnium oxide memory store, but you can see that on-off ratio becomes better than the room temperature, right? That means it becomes better, like the performance becomes better. The read operation will be more reliable here at 10 Kelvin. Similarly, in 4 Kelvin, you can see again, all the performance metrics actually becomes worse. So you see like lower on-off ratio, so worse read operation here. And also you see that set voltage and reset voltage both increases. That means if this switching threshold increases, both of these increases, you'll have to use higher or larger write voltage, right? Compared to the previous case. So you will need higher write power consumption. So from like, if you summarize all this for memristor, actually, if you go to lower temperature, their performance actually becomes worse. Okay. Then we have these ferroelectric memories. So in ferroelectric memories, we have two types of memory. One is the ferroelectric capacitor, where you have this simpler structure, metal ferroelectric metal structure, like the memristor. And we have another one, which is ferroelectric FET, where you have the same structure like the transistor. But if you remember, in the MOSFET or any other transistor, you don't have any ferroelectric material after the gate, right? You have only gate, oxide, and then the channel, semiconductor. But in ferroelectric transistor, you have this ferroelectric material between the gate and the oxide here. So these are the two types of memories. And again, Dr. Aziz will cover more details about ferroelectric memories. I'm like going from very high level perspective here. So in ferroelectric materials, you have this type of polarization versus voltage characteristics. Okay, so polarization again is related to the charge density. So if you have the charge in this ferroelectric material, if you divide the charge by area, that's your polarization. Okay, so you can say like charge per unit area is the polarization here. So for ferroelectric, again, you see this is non-volatile. That's the major advantage here. Even if you remove the voltage, it has two polarization states. One is positive, one is negative. So even if you remove the voltage, it can remember what polarization state it was in. It was either in negative or in positive. And write operation is similar to memristor. You need to apply either a positive voltage or a negative voltage to switch to the positive and the negative polarization state here. So this is your write voltage. And for ferroelectric FET here, for these two polarization states, negative and positive. So this is for negative and this is for positive polarization. So based on the polarization state of the ferroelectric, the threshold voltage of the transistor will actually become different. Okay, so if you have lower and higher, they are actually named as low VT and high VT, two different conditions for ferroelectric FET. Okay, so if you have low VT and high VT, that means this condition, the transistor will will activate faster, right? Faster than the other condition where you have the higher threshold voltage. And now if you select a voltage from like this range here, you will see that the polarization state where you have lower threshold voltage, you will get higher amount of current because that has turned on. But the condition where you have the higher threshold voltage, that's still off, right? So you have this off current here. So you have a large difference between the channel current of this ferroelectric FET for the two polarization states of the ferroelectric material. So that's your read operation here. If you can detect like the change in the channel current, like either it is off or not, that's your read operation for the ferroelectric memory. And again, this memory is non-volatile, as I explained. If you remove the voltage, it can remember its polarization states. And similar to memristor, it's again, their speed is higher. They have like high endurance and long retention time, right? So you have all the advantages there. And so again, people take the same ferroelectric FET they used for room temperature, and they measured at different temperature down to 6.9 Kelvin here. And they reported that this memory window actually increases at cryogenic temperature. So by memory window, they means this width here. This width is the memory window. Okay, so how far these two polarization switching curves are are away from one another. Okay, there's the memory window. So they mentioned that this memory window increases at cryogenic temperature. So if you have like larger memory window, that means that your memory system will be more reliable, okay, more robust to external variation. But again, if you have wider memory window, for example, if this blue curve comes here and if this red curve goes there, so you have higher memory window, but you see the switching thresholds here, they both actually increase, right? So if they are known as like coercive voltage for ferroelectric or program erase voltage for memory system. So if if you have larger memory window, that's good for reliability, but again, that's bad for the write operation. Because if you have larger switching threshold, you will now have to use like larger write voltage, larger program erase voltage for this memory. So that will again increase your write power consumption. So this is also known for like room temperature application. This trade-off is there, and you see at cryogenic environment that becomes worse because like for ferroelectric memory systems, the memory window is still like the memory window that we have is enough. So it's sufficient. We don't need to improve that like anymore. But the problem is when you go to cryogenic environment, this program erase voltage actually increases. So that's bad, right? So compared to room temperature, their performance actually becomes worse here. And then there are many works who actually take only ferroelectric materials, not the ferroelectric capacitor or ferroelectric transistor. They only took the one like the standalone ferroelectric material, and they characterized them at different temperatures. And also they reported the same type of behavior. In some cases, their coercive voltage or the switching voltages actually increase. And for one anti-ferroelectric, which is not ferroelectric actually, like anti-ferroelectric material, that in that case that decreases, because for ferroelectric, if that increases, for antiferroelectric that will decrease, right? But for most of the ferroelectric materials, their coercive voltage actually increases. That means you will have to apply higher voltage for write operation here. So that's already a challenge for room temperature, because for ferroelectric you will have to apply like 2, 3, 4, even 5 volt of voltages for write operation. And if that gets worse at cryogenic temperature, you see, so there will be like huge challenge there. And then we have this spintronic memories. Dr. Aziz has not covered spintronic yet, I guess, right? He did? Okay, you already know about them, then I'll skip this. So you have these two magnetic layers, right? One is free layer and another is spin layer. And you have this, like you can say relative spin orientation. You have parallel or anti-parallel state. And for these two states, you have two resistance states like the memristor. So you have from high level behavior is similar to memristor, but the underlying mechanism is different. That's the only thing. So again, you know all these things, I guess. So people have again take the, for spintronic memories, the magnetic tunnel junction is the primary building block, right? That stores your data, and you have one transistor there. So transistor always becomes like better at cryogenic temperature, but they only took the magnetic tunnel junction and measured at cryogenic temperature. And for one of the major challenges for spintronic memory is their resistance ratio, right? That's the biggest challenge, because you have inherent like a ratio of 2 between the two resistance states, and that's one of the major challenges for spintronic memory. And it has been reported in most of the works that when you take them to cryogenic temperature, that ratio becomes better. So that actually improves at cryogenic temperature. So I think we're at the end. So I'll keep this topological memory because that's completely different. I will keep this for next class, but I will quickly talk about the challenges of non-superconducting memories. So we have covered the charge-based SRAM, DRAM, flash, and the memory state spintronic and ferroelectric memories, right? So these three and this. So all of those are non-superconducting room temperature memories, and we have seen that in most of the cases you might have the idea that in most of the cases performance actually improves, right? So everything gets better. Then why do we need like superconducting or other cryogenic technologies? Why can't we just use like SRAM, DRAM, flash, because they become better, right? But the challenge is their power consumption, right? So in non-superconducting technologies, the VDD is still at like 0.7, 0.5 volt, and as I explained, the energy, the best energy like efficiency you can get is like in picojoule range. From this non-superconducting or CMOS-based memory system or any circuit. But the challenge is like when you go to this low temperature cryogenic environment, I mentioned we need to use cooling refrigerator, right? And we need to keep supplying that coolant, like for 77 Kelvin liquid nitrogen, for 4 Kelvin it's liquid helium. So you'll have to keep supplying to keep that temperature at that range that we want, right? And that's why we have a power limit for each of these temperature ranges that we can afford. For example, if we are at 10 Kelvin temperature, the power limit is 100 milliwatt. And you see, within this power budget, the scalability of the non-superconducting or any CMOS circuit will be limited, right? You cannot like limit it. And now, if you want to use this CMOS control processor and CMOS memory for quantum computing applications, for example, then if you have a limited size of the control processor or memory, that will not be able to control like thousands of qubits, right? That will eventually limit the number of qubits. You see, that will end up being the bottleneck here. So that's one of the major challenges why we cannot use like non-superconducting or room temperature memories directly at cryogenic for all these applications. And another challenge is their speed. So as you have seen, like for memory strip, spintronic, ferroelectric, all these memories operate at like nanosecond switching time, right? Which gives you like gigahertz frequency. But to give you a like perspective, the superconducting device which are used to design like qubits for quantum computing, they operate at hundreds of gigahertz frequency. So you have a like 100-time mismatch between these two technology, right? So if your memory works at like 1 gigahertz and if you have qubits which operate at 100 gigahertz, so these are not compatible at all, right? So that's one of the major challenges. So this power consumption and speed, these two become the final bottleneck why we cannot use these non-superconducting and room temperature memories for all these cryogenic applications, okay? And then these actually motivates to take us to the next topic of this uh, like class, which is the superconducting, why we need superconducting or other approaches, okay? So I think it's a good place to stop, okay? So I hope I'll see you in the next class, okay? Yeah, sure.
Question, can you upload the slides for us?
Yeah, I'll share this with Dr. Aziz. I don't have access to.
Oh.
Yeah, I think he will upload it. Yeah, sure.
Yeah. We started on it. Did you get past that first like error about the